D raised to dx into 0.
Isha.
Hello. Hello.
Yes, sir, you're audible.
Okay. So yeah. So sorry for being late. So yeah. So before I start today's class, any questions, any doubts about whatever has been done till now? Okay. So if you don't have any questions, that's excellent. So
Sir, hello, sir.
yeah.
Yes, sir. Sir, actually, I didn't attend the last class because of some problem. So I was studying the base first search myself, and I was having some difficulty. So can
Okay.
I ask that
Sure.
question?
Yeah.
So in the base first search in the Coreman book, there is a portion called base first tree. I didn't understand that actually. Base
Wait
first
for
tree. Base first tree.
base first tree. Yes. When you do a base first search, right? Look at the edges through which you are discovering new vertices. So every
So
vertex
can you
that you
please explain it pictorially? Then it will be very clear for me.
okay, so it is there uploaded in the so in the video that has been recorded and has been uploaded. It is there. We have spent just
Okay,
so
okay,
did
sir.
you follow the depth first thing?
Yes,
Right,
yes.
right,
But
right.
actually, I didn't able to get the picture of the base first tree.
No, forget the breast first tree. What about depth first tree? You
No,
understand
but the
depth
tree portion was not clear. So the
where is
video
there
was
in
not
the depth
uploaded
first?
yet.
The depth first search has been uploaded 3 days, 4 days ago, or 2-3 days ago. Have you gone over
Actually,
the
my
depth
phone
first?
was stolen, so I didn't get the chance to watch that. I will do that today.
Okay, so where are you now actually?
I am in hostel right now.
Okay, so but your phone was stolen. That's okay. We understand that very much. You could have just attended the class by sitting in the classroom also, right?
No, I was in the police station the last day for
Yes,
filing
but what about
for
the day
filing
after
the
that?
video.
Day before that? You are not in the depth first tree also.
Yes, I was there in the class.
So in the depth first tree, we had discussed depth first tree there. Did you follow
Yes,
depth first tree?
I did that class.
Did you follow depth first tree?
No, I read that, but some ambiguity are there. I have to check that again.
Okay, I mean the depth first tree and the breadth first tree are basically same thing. I mean same thing meaning the concepts are similar. When you apply the depth first algorithm, the edges through which you are discovering new vertices, they form a tree. That's if you run the depth first algorithm, that's the depth first tree. If you run the breadth first algorithm, we do the breadth first tree. So I mean, my question is that we have spent 2 classes on this thing. One is depth first, one is breadth first. One on the last Wednesday, one on last Monday, which is day before yesterday. So if I understand correctly, you are not in both of the classes, and that's why you are not understanding what this depth first tree or breadth first tree is. Am I correct?
Okay, I have to go to the class once again.
Yeah. So Shashwata, so you are in MTech CS or MTech CRS?
CRS.
Okay. Yeah, because there was a time when MTech CRS students were just not coming, and while everything is being uploaded online, I mean the reason I am doing it and not just uploading the videos of the last set of lecture notes or something like that is because I want you guys to attend, ask questions. If you are not going to come to the class, then you will struggle. Of course, if you have doubts, very much ask me. But if you have doubts on things which was discussed in class and you have no idea about that, that doesn't sound right. Ask any of your friends who comes here regularly in this class. This depth first tree and the breadth first tree we have covered in quite a details. If you have doubts, do ask me. I will surely answer it. But it seems that you have just not You don't know it because you have not
See,
completed.
yes, I didn't attend the last class. The base first search I didn't attend.
I am asking about the depth first. The
I have
depth first-
attended, but there was some conceptual question about that, but I didn't get any chance to ask you because I was not attending the last class.
But then did
So
you
if I
understand
attend the
depth
last class,
first
then I
tree?
would ask.
Then you understand depth first tree. There is a concept of depth first tree. We have discussed this one in very much details in on Wednesday, last Wednesday. If you have doubts on that, very much ask me. But if you say what is that, then I'm not
No,
answering.
no, I'm
that.
not asking the what is that.
I mean, because that's what you are asking for the breadth first tree. If you have understood depth first tree, then there is no way you understand not understand what is breadth first tree. I'm not talking about last class. I'm talking about the last Wednesday's class, which we did depth first algorithm, and in that case we have the depth first tree. So anyways, any other questions?
Sir, I have one question regarding the assignment. Can I ask it here?
Yeah, sure.
So in the question number 2, it was given to sort an array where the elements of the array ranges from 0 to n cube minus 1, and the length of array is n. So there is no mention about the base of the elements. But we have to sort it in the linear time. So should we assume it to be the base to be order of n, or exactly n like that?
So see,
Otherwise,
these are the numbers between 1 to n cube. Okay. That's all we are saying. You can choose whatever base you want. I mean, number is between
0 to n cube minus 1.
0 to n cube.
Yeah.
Okay, this has no base involved in it. When you are representing it, you can represent it in either binary, tertiary, decimal, or some other base. Maybe
So,
even
sir, in
base 10.
the time complexity, you're not going to include the cost of converting it to a different base.
It would not take that much time.
I see.
Okay. I mean, just we are like,
Can we assume the base to be n? Like, is it
Okay.
fair enough to do that?
I mean, you can assume the base to be n if you want.
Okay. So there won't be any deduction of marks if I assume that.
I mean, no, that's fine. You can use the base to be n also. But
Okay.
Yeah, believe me, it will not help you. I mean, it will help you, but I mean that the assumption is not something required. Let's put it this way. Anyways, first do it with that assumption, and then
Okay, sir.
you will see.
Okay.
Yeah. So when is the due date? On this Friday, right?
On Sunday.
On Sunday, yeah. Okay. Yeah. Also, we will post another problem set. Basically, particularly on DFS, BFS, and the spanning tree, minimum spanning tree. This weekend. So that's a problem set.
Sir, you are not audible, I think.
Oh, am I not audible? Hello, am I audible now?
Yes,
No,
sir.
sir,
You
you
are
are
audible.
You are, but it's a little quiet, that's it.
Oh, okay. Is this better? Hello, is this better?
Yes, yes, slightly.
Okay. Should I continue or should I change something?
So please continue. You are audible.
Okay.
It's okay. It's okay.
Okay. So we will be trying. We will post a problem set on the BFS, DFS, and MST kind of algorithms. Okay, of graph algorithms basically. And please, so that's the problem set that is we have, and we might also give you a small assignment to be submitted before the NSEM or something like that. So that will help you to, or maybe after the NSEM, whatever. So that it will help you to prepare for the NSEM. The NSEM is also not too far away. So I
You
think there
mean
is
them, right, sir?
midsem. Yeah. So there's only 3 more classes there that we have. Okay.
Sir, we are planning to schedule our midsem on 6th at
That's fine.
Wednesday in second half.
Yeah. Okay. That's okay.
Okay.
That's perfect. Fine.
It will be offline, right?
It will be offline.
Yeah. Thank you.
So of course you are having the tutorials. Please come to the tutorials. Ask your TAs. Solve questions. The reason we are posting problem sets is that you solve questions. The problem with this course of algorithms is that I can only teach the high level picture. Okay, I can only teach the basics, and everything will look very simple if you just attend my lectures. But unless you try to solve the problems, you will not get the habit of thinking algorithmically. Okay. So I really encourage you guys to try to solve as many problems as you can. If you can solve problems from outside the problem sets or the assignments that we have given, if you have doubts on any of those problems, you can take them to the TAs or bring to me also, for that matter, both physically or in class, and we will be happy to discuss. Okay, problem solving is the key to understanding or mastering algorithms. Okay, yeah. Okay, any other question? Any other doubts? Something? Okay, so if not, am I audible?
Yes,
Hello?
sir. You're audible.
Okay. So let me start with what we did in the last class, or where we ended in the last class, basically. Basically, why am I not able to connect? Yeah. So in the last class, we kind of asked you guys to go back and think about the various properties of the MST. Did you guys do that? Did you guys manage to prove that? Hello? Am I
Sir,
not there?
like I did not, because one of the issues is that without the slides, it like in online class, it's really hard to take notes simultaneously. So
Okay.
like, yeah, so we could not get the references to refer from. Like I studied an overview, but did not exactly remember the things. So that is one of the issue I'm facing.
Okay. Okay. Well, what about the rest? Okay. So if you, so maybe I can start from here. Just one second. There's some issue regarding this stuff. So okay. So let me just tell you where we were. Maybe let me share my screen. And oh God, where is it gone? This was something weird happened. I have no idea what's happening. Anyway, so our job was to find the minimum spanning tree in a graph. Yeah, and we wanted to design an algorithm for that. So the first thing that was okay, so let me just quickly, for people who have kind of missed the concept of minimum spanning tree, maybe who are not there. So basic idea is that, so I don't want to go into this motivation. Of course, there are lots of motivation for this problem. We have already done that. But you have been given yeah, a weighted graph, right? You have a set of edges and a set of vertices, and you have weights on the edges. And our job is to to construct a minimum spanning tree. So that means I produce a spanning tree, okay, such that, okay, what is a spanning tree? A spanning tree is, of course, you have seen it in your earlier courses. It's a tree that connects all the vertices of the graph, right? And we want to minimize the sum of the weights of the edges. So for example, here we have this graph in which we have vertices and edges, and every edge has a weight, and our job is to find a spanning tree. Now we can of course have spanning trees. For example, this is a spanning tree. Now once we have a spanning tree, let's look at the sum of the edge weights. So for example, this is 8 plus 9 plus 5 plus 15 plus 6 plus 11, right? So this is a spanning tree, and the spanning tree has weight 54. If you add them, you will get this number. Now there can be other spanning trees, right? For example, I can, so instead of connecting things like this, I can construct this spanning tree. So this is another spanning tree. So this spanning tree has weight 45. So similarly, we can have all the various spanning trees, and every spanning tree has a associated weight with it. And our job is to pick the spanning tree with the minimum edge weight. So in this case, it so turns out. Yeah. So in this case, it so happens that this particular spanning tree of weight 39 is the minimum. Yeah. Any questions? So the problem that we want to solve is that given a weighted graph, okay, and we will, as we have discussed earlier, we will think of the weighted graph as given as a adjacency list, and the job is to find a minimum spanning tree. Okay, so although it is written the minimum spanning tree, actually there might be multiple other minimum spanning tree. You can have more than one minimum spanning tree, particularly if the edge weights are not distinct. So how do you go about it? Okay. Now, the thing that we kind of observed, let me just see whether something has come out here or not. Just one second, let me just see one thing. Something is not working. Why is my iPad not connecting? Just one second. Maybe I will connect it from. Sorry. Something I have made a mistake. Okay. Oh God, this is not good. Just one second. Let me connect to Zoom through some other. Okay, so maybe so maybe let me join through some another account so that you can then you can then I can then just try to write something.
Okay, sir. We are waiting.
Recording in progress.
Hello.
Yes, sir. You are audible but echoing.
Yeah. Is now better?
Yes.
Yes, sir.
So in the I have joined in another 2 different accounts. Can you see my other account?
Yes, sir.
Yes, sir. The screen is started saying.
Yeah, so yeah. Can you see my some screen or something? No.
It's still buffering.
Buffering. Something is not working. What is not working? Okay, so let me start with the whiteboard. Okay, now you can see my screen, right?
Yes.
So our job is to get a MST, right? So we have a graph G, and the weighted graph. So there is a edge weights, and our job is to find an MST. So how would you go about doing it, right? Now, in the last class, we kind of discussed what can be the first step. Okay. Now, first step is that I want to pick edges one after another, right? So that is one possible way of doing it. I want to pick up edges. Now, what do you think? So, question is that I want to pick up an edge, right? So my job would be, if I have to create an algorithm, I have to pick an edge E and hope that I am fine. What do I mean by that? Let's see, if I end up picking up an edge in my tree, or as a candidate for one of my tree edges, and there exists no spanning tree containing that, or no minimum spanning tree containing that edge, then I am doomed, right? So what is it that we would be doing? Our hope is to pick an edge which such that after picking that edge, I am still guaranteed that there exists a minimum spanning tree containing that very edge. Okay, so what it means is that I want to say that I hope, meaning that there exists an MST containing E. So this is a natural way of starting an algorithm, right? I do a first step, okay, and hoping that I am not already doomed, that I can complete the process, right? So what do you think would be this first edge that we pick?
So shouldn't it not be the maximum weight edge?
It should not be the maximum weight edge. That's very true. Maximum weight edge might not end up helping me. If I just pick a maximum weight edge, then there are, so for example, if the graph is if all the edge weights are distinct, then you can prove that, this is one of the questions that was asked in the last class. You can prove that there does not exist any MST, any FLST containing the maximum edge weight. So that means if I pick the maximum edge weight, then I am clearly doomed in the first place. So what is the next candidate? Yeah.
But in the previous class, you told that it's possible that minimum spanning tree might include the maximum.
Might,
Yes,
but
sir,
might
if it's
not.
just a tree. Sir, if it's just the whole
Yes,
thing is just a tree.
Exactly,
then-
but think that I'm talking about in a general setting, right? It might include, but it might not also,
Okay.
right? I have to kind of guarantee that whatever may be the graph, I should be able to complete this algorithm.
So the smallest weight age will work for the first step.
Right.
It's not guaranteed, but that's our best bet.
So it is not guaranteed. Somebody said it is not guaranteed. What do you mean by that? It is not guaranteed.
Well, it could happen that choosing the smallest edge, then all the eventual edges that we get in our minimal spanning trees are much larger, and that will create a problem later on.
Okay.
Just
this
we don't have.
is-
Yeah.
Yes, good. That is a very much a possibility, right? So that is exactly the reason we need to prove something. Okay. And two of the things
Sir.
that we, yeah,
So
go ahead.
MST would always like for any minimum weight age, we can have a corresponding MST that we proved in the
Right.
last class in some sense,
Good.
right?
Very good. So in the last class, what we had
Yes,
proved
This
is
will always
that,
be there. Yeah.
that yes, there can be MSTs that doesn't contain the minimum edge weight, but if E is the minimum edge weight, minimum weighted edge, right? Minimum weighted edge. Then there exists an MST containing E. So this is you can think of it as a theorem. We had kind of discussed this theorem in the last class. Okay, and I leave it to you guys to go back and formally see it. Or we kind of almost did it is in some amount of formality also. So what this means is that yes, I am not guaranteed. I'm not saying that every MST contains the minimum spanning, minimum weightage, but at least the first weight age, the minimum weightage, if I pick it, I am not doomed, because I would be, there is a chance of me completing this algorithm, or completing the algorithm meaning completing the MST, because that, I mean, I am not completely left with that. Okay, there is no MST with this edge. So there are some MST, and we can continue with that. Okay. So if you think in that direction, okay, so sorry, let the first algorithm be, first edge that you pick be the MST, be the minimum spanning, minimum edge weight. We are still fine. Is this clear that we are not still completely doomed? If I pick the minimum spanning tree, the minimum edge weighted edge, we are not doomed yet.
Yes, sir.
Okay, good. Now the question is that what happens to the next step? What is the next edge that we can take? What is the next edge that we can take?
We first, after the first stage, we
Hmm.
reach the vertex and see which is the minimum edges emerging from that vertex, and we take that one.
Okay, so that is something that you are saying, that what we can look at is we can take the minimum edge weight, look at a vertex, and that vertex must be connected in some form, right? So look at the
Yes.
We have
minimum.
to check.
Yeah.
We have to check that if that edge is making any cycle or not also.
Hold on. So you guys are two of you are telling two different algorithms. Okay, we will do both of the algorithms. in the first person who told, you are saying that, okay, we have got an edge, we are guaranteeing that we are fine. Now you take a vertex and slowly grow the tree. Consider that vertex or vertices, two vertices, and look at the edges that are emerging from these two vertices and consider the lowest of them. Now, yes, if that works, excellent, right? That is one way of doing it. So you continue by growing the tree slowly. And another way is that we might want to, the next thing to kind of say guess is that, okay, the minimum age is there in an MST. Maybe using a similar argument, I can also say that the second minimum is also there in the tree. So this is a statement that I want you to kind of prove. Okay, so this is, I am not going to, I mean, I'm going to prove a more general statement later on in this class. Later on in this class, meaning today only. But basically, what I'm saying is that, so let sorry, E and E prime be two of the least weighted edges. Weighted edges. Okay, so then, so of course, I am not saying that the weight of E and weight of E prime are distinct, but they are the least. If they might be same, but they not be different. I don't know. Okay, prove that. So you can think as a theorem also that if there exists an MST containing both E and E prime. Of course, we know there is an MST containing E, the least state. I'm saying is that there is an MST that containing even E prime. Can you prove this statement? I'm hoping that all of you has a pen and paper with you somewhere. Can you?
Yes, sir.
Sir,
Yes, yeah.
can I proceed regarding, like, in somewhere the last proof that we did for the minimum
Mhm.
edge is
Mhm.
basically a circle must have at least 3 edges in it. And if we are considering the 2 least edges, we can remove the third one always from a circle and get them. If they're in 2 different circles, then it's not an issue as it is. If they're in the same circle, even then there must be a third edge that
Very
is
good. You have got the idea completely right.
observed.
Excellent. But maybe let me give you friends 2-3 minutes. Why don't you guys try to prove this statement? Okay, it is, as your friend says, it is very similar to what we have done in the last class. Okay, so prove that even the minimum 2 edges also is contained in some MST. So once you are done, maybe you can just either raise your hand or send a message or something like that. Once you have.
Sir,
Yeah.
sir, if we have a subgraph of a graph,
Mhm.
so the minimum spanning tree of that subgraph will extend to form the minimum spanning tree of the whole graph. Is that true?
I mean, that is true, but that's not obvious at all. Actually, no, that's not true. That is not true. No, that's not true. I'll give you an
So
example.
what was the question?
So if so what he asks is that if G prime is a subgraph of G, okay, and so I find a MST of an M is a sort of say T is an MST of G prime, then can T be extended to get a, then T can be extended to an MST of G. So this statement is not true. That's what I'm saying.
Sir, just take an edge which is not in G. Okay.
Mhm.
Which is not in the MST of G. Then just consider the subgraph containing the two vertices and that edge only.
Right.
Am I clear?
So what are you trying to do? You're trying to disprove this statement, or you are
Yes,
proving
sir.
this statement?
I'm trying to disprove it.
Yes, go ahead.
I am trying to get a G
Mhm.
and let there is a edge of maximum weight in
Yes.
G. Okay, and I will consider G dash as that edge only, containing that edge and that two vertices only.
That's true. That's good. Yeah, you can talk about that. Yeah, that will do. Yes, good. I mean, maybe if I want to kind of draw a picture more of this thing, so let me just draw it for. So say you have a say the G prime is something like this, okay? And what is G? G is something like this. Right? So these things can be 100. All of them has age 100. And all of them has 1. So G prime MST will be always be having ages 100, right? But G is a MST, all the G's MST, they have only unique MST of G. Yeah. So is it clear? So who asked this question? Venkatesh?
Yes, sir. Yes, sir. It's clear, sir.
Yeah. So what about to this thing, this question that I asked here?
So one more thing.
Yeah.
Every MST will have this least weight edge, right?
No. I mean, see, okay.
Means if it doesn't have, we can form MST with that edge, right?
Exactly, because there can be multiple edges with the same least weight, right?
Yes, sir. But if we don't have that, then we can by the last class theorem, not theorem, we can do that.
Yes.
If we add the edge, then it will be a cycle. Then we can replace that. So if we remove that edge, I am thinking in this it will work or not. If we remove that edge, that least weight edge, then okay, we don't know that E dash is the least weight for that edge, for that removed graph.
I mean, that will be, of course, because E dash is the minimum, second minimum, right?
But it might happen that there might be 2-3 edges with having E as the
same.
Weight.
Yes. Yeah. So see, I mean, the algorithm is very simple to what we did. Okay. So by whatever
we will just E dash in the MST and then that must create a cycle,
Right,
and a
exactly.
cycle must contain at least
Very
three edges.
Exactly. Yeah. So first of all, using this thing that was written above, right? Here, we know that there exists an MST containing, there exists a MST, let's call this one T, containing E. Let me know. Now consider I add the edge E prime to that T. What happens? When I add an edge to a tree, I get a cycle, right? And in that cycle, I can just take out any edge and remove it, and I'll get back another tree. Now there must be a cycle, and every cycle is of length at least 3. So there exists a cycle of length greater than or equal to 3. So one of the edge is E prime, maybe the another edge is E, but there must be a third edge in that graph, right? If there is a third edge in that graph, okay, so that means there exists an edge, the E double prime, in the cycle, because that E double prime is not equal to E and E prime. So by this definition, if I remove this E double prime from this graph, then what is this? This is
So wait a second. I don't follow why you claim that E double prime can't be, like both the other two edges can't be E. Why is that?
No, I'm not saying that. So once you add a edge E prime, you get a cycle, right?
Yes.
In that cycle, how many edges are there?
At least 3. Yeah.
Okay. So one of the edge may be E prime, right? Or one of them is E prime. Maybe another edge is E. So that means there must be a third edge, right, in the cycle.
Sir, if both the weights of the other two edges are the least one.
No, forget all of that. We'll come to that.
Okay.
Will there be an another edge?
Certainly. Yes.
Certainly, right? So let's call this one E double prime. Okay. Now, what is the weight of the E double prime? Okay. See, E and E prime are the lowest two edge weights. That's by definition. So E prime can be of the weight. E prime's weight can be equals to E double prime's weight. That I agree. But it cannot be too much more, right? Sorry, too much less. E double prime's weight must be bigger than or equal to weight of E prime.
Sir, E prime is our second smallest weight, right?
Yes.
So what if weight of E double prime was weight of E, which is our smallest weight?
No. I don't mean the second smallest weight, mean the sense of distinct weights.
I see. Ordered. Okay.
Ordered.
Okay, then I follow. Yeah, sure.
In the ordered thing, okay. Yeah. So yeah. Right. So now I will just take this tree, add this E prime, remove V double prime, and I get a tree, another tree, and the weight of that tree is less than or equal to the original tree, which was an MST. So this must be an MST also. So that means there exists an MST of weight, the minimum of the containing E and E prime also. Correct? Any confusion with that? No.
Sir, can you explain again?
So which part? Can you just be a bit more precise?
Sir, actually, we are having a cycle. That's okay. Cycle of length 3.
Yes, there's a cycle of length 3. Okay.
So that cycle contains E dash.
That contains E dash. Maybe it also
contains.
Yes.
Hello.
Yeah. Go ahead.
E dash, and there will be 2 more edges.
Yes, one of them can be E.
one of them can be E. We
Can
don't know.
be. I don't know. We don't know. But more importantly, there is a third edge,
Yes, sir.
right? The third
So
edge is
then
no, third edge is called E double prime. Okay.
yes,
E dash
yes.
dash. Okay. So that third edge is not E or E prime.
Yeah.
Okay. So I consider, so I have added with T. So with T, I have added E prime, right? After adding E prime, I created the cycle. From that cycle, I am picking up an edge, which is E double prime, and removing it. So the resulting graph is back to a tree.
Tree, sir. It's a tree.
It's a tree, right? Now, what is the weight of this tree? What is the weight of this tree?
Either same or smaller than the previous one.
Yes. So I have added E prime and removed E double prime. So since E double prime is neither E nor E prime, it must be something whose weight is more than or equal to E prime. That's by definition of E and E prime. So therefore, I have added something, removed something. I have removed something which is possibly more. So the weight of this tree, T prime, the weight of this tree, T prime, is less than the weight of T, less than or equal to the weight of T. Is this clear? Venkatesh?
Yes, sir.
I mean, if you want, I can go over it once again also.
No, actually, I got this up to it is a tree.
Yes.
Then you are telling that weight of then the minimum spanning tree. What happened to minimum spanning tree?
Yes.
So since we took with minimum spanning tree, so it will be same. The weight of that tree will be same, or
Yes.
it might increase.
It might decrease. Decrease. Because see, I have added E prime.
But if it decrease, then it won't be MST, right, sir?
Yeah, so it cannot be decreased. So it will remain same.
So it will remain same. That we can consider, but it won't decrease.
It will not increase. Let's put it this way, it will not increase. That's all I care.
So then if it won't decrease, then the weight that you swapped it with must have been identical to one
Yes,
that you.
yes,
So
that's
E
how
prime
that's
prime
what
and
it
E
will be.
prime.
Yes.
Yeah.
Yeah. So I mean that is following out, but for our purpose, all we have to prove is that the T prime's weight is lower than or equal to the weight of T. That's all. And it cannot be strictly lower than T. It cannot be. So then that would be a problem with the definition of T, MST. So that means weight of T prime must be equals to weight of T.
Sir, that means that initially it wasn't an MST, the tree we chose.
Sorry.
Initially, the tree we chose containing the edge E wasn't an MST.
That was an MST. That was an MST.
The only thing it means is that E prime prime is equal to E prime.
Yes. So what will happen is that E prime will be equal to E prime. That's the only option.
Sir, can we extend this to case of 3 and then 4?
Yes, why not?
Minimum least weighted edges. Like we can keep on continuing this, right?
No, but sir, in that case, your smallest cycle, because it is 3.
So the only problem is that a cycle might start coming up, right?
Mm-hmm.
But exactly that's the algorithm that we have. Okay, so let me quickly swap. So let me quickly share my another screen. Yes. So I am going to now give you the algorithm from the Kruskal's. So this is called the Kruskal's algorithm. Is exactly what we kind of would build up to. The idea is that pick the minimum edge possible at any point of time. Pick the minimum edge weight. Let's start. Then every time you try to pick the minimum edge weight if possible. What do I mean by if possible? See, if all the edges are same weight, then everything is minimum, right? Then that's a problem. Of course, I can pick up any one edge. I can pick up any two edges, but the third edge might create a cycle. So if possible means that as long as they don't produce a cycle, you pick it and continue like this. Let's see what can be done. Okay. So for example, this is an algorithm that was there, right? So what is the minimum edge weight here? It's A to D, right? Or C to E. So you can pick any one of them, doesn't matter which one. So here I picked up A to D. The next one, what is the minimum edge weight? C to E. Does adding C to E produces a cycle? No. So I just add it. Which is the next one? It should be D to F. Does it produce a cycle? No. So I pick that. What's the next one? A to B. Adding it, does it produce a cycle? No. I add it. What is the next one? The next one is B to E. By adding it, does it produce a cycle? No. I add it. What is the next one? It can be either B to C or C to E, F. But if I choose C, E to F, by adding it, does it produce a cycle?
Yes, sir, it does.
Yes. So I cannot pick it. So I don't pick it. I move to the next one, which is B to C. Does it produce a cycle?
Yes.
Yes. So we cannot pick it. We take the next one. Which is the next one? So maybe I pick B to D. That's the next one. Does it produce a cycle? Yes, that also produces a cycle. We cannot pick it. Okay, what is the next one? E to G. Does it produce a cycle? Oh, yes. It doesn't produce a cycle, therefore we pick it up. And that's the end of the algorithm. Okay. Now, this algorithm is what is something called a greedy algorithm. It's like we just, our intuition told us, see, I can start with picking up the lowest weighted edge. Then I can pick the second lowest edge, weighted edge. Maybe we can continue like that a few times. And after we are done with doing it a few times, then maybe we'll get, as long as we are not producing a cycle, we continue. And let's hope that it works. This is a very typical way of solving many problems in modern day, in modern computer science. Okay, this is called greedy. You make the first few steps, first few observations, and you kind of say that, okay, why not? If the goal is to create the smallest MST, why don't we just greedily pick the smallest edge? Now, greedy algorithms are not necessarily always correct. This is a greedy algorithms is used. So I don't know if anybody of you have ever designed algorithms for say machine learning or something like that. You guys possibly have seen greedy algorithms being applied in various contexts, where you do what your intuition says you to do. Okay, it seems to be, I mean, this should work, or I mean, this is the right thing to do, right? And you continue like that. Now, I know that some of you had done optimization course in the last semester. In optimization also there is a concept of like this gradient descent and all those things. And again, that's some kind of a greedy algorithm. You kind of greedily move. But of course, greedy algorithm has a problem. You can get stuck somewhere. It might not be correct, right? So this is an algorithm that's a greedy algorithm. Intuitively, it made sense for the first few steps. Now, question is this algorithm correct? Is it actually producing an MST? The algorithm, it's almost clear that this algorithm produces a tree, right? But why is it an MST? So what would be the pseudocode of this algorithm? This will be kind of very simple, right? Sort the edges in some ascending order. Oh, sorry. So forget this. In these two steps, forget this one. Okay. So initialize with an A, which is empty. So these two lines are not required actually. Then sort the edges in an ascending order by weight, and you go over them. As soon as you get a particular edge in that order, if adding that edge to the set of selected edges, so A is the set of selected edges, right? It doesn't create a cycle, then you add it and output the algorithm. And finally, when you're done, you output the set of cycles. So is this algorithm clear? What the algorithm is doing? Forget the correctness for now, but is the algorithm clear?
Sir, I had one query.
Yeah.
Hello. So, like, we were dealing with graph representation in terms of adjacency list, right?
Right.
So, from there, we defined whenever we had weighted edges, we would just define a structure and store the, like, along with the destination vertex, we would also store the weights. But from there, in this case, we have to collect all the edges and then sort them accordingly. Like, how is that part being performed?
Yes. You have to collect all the, so you have to produce another list in some sense, okay, of all the edges. Okay, so that list will be of size M.
Okay.
Right.
So,
then you put all the edges according to the their weight and then order them.
Okay.
Yeah. Right. Any other questions for this particular algorithm? Okay. If not, then let's move to the correctness of this. This is a very important thing. This is an algorithm where correctness of this algorithm is by no means obvious. So this is something very different from all the things that you have seen so far in the world of, say, sorting and so on, right? In the sorting algorithms, correctness of an algorithm was kind of obvious in some sense. I mean, you wrote something, but that was like, okay, maybe look at the pseudocode and it should be clear. But here it is no way obvious. Yeah.
In this algorithm, we are not going like a chain, right? We are
going like a chain. Yeah, you kind of a chain you can think of if you the ordering in the ordered set. Yeah.
No, it's not like that. We are ending at a vertex and starting from that vertex in the next move.
No, we are not.
It's not like that, right?
No. We are not going in a chain. And in the intermediate state, the set of all edges selected in A need not be connected.
Okay.
Okay, but only at the end it should be connected. Okay, so good. So let me. So when you prove the correctness of this kind of algorithm, say for this particular algorithm, we have to prove three things. Number one, or first two things is that the algorithm is the output is a tree, which means the output must be connected, and it must be a acyclic graph. And thirdly, which is the most hard thing, to prove that it's an MST. So once we prove these two things, that means it's a tree. But why is it minimum? Okay. Now the first two of these statements is kind of easy. So let's see what. So output is graph is connected. Do you guys want to take a shot at this? Try to prove it. How would you
So-
formally prove?
At any given step, we check for cycles. We
Yes.
can prove it inductively. Suppose at n minus, suppose it was not a cycle till n minus first step. And then at nth step,
No,
we check-
no. Which one are you trying to prove? That you're trying to prove that it doesn't have a cycle, right? Is that
Oh,
what you're
sorry.
trying to
Yeah. You asked for connected. Sorry.
Yes.
Yeah.
No, good. So maybe you can, since you started it. So let me just. So this is true that it doesn't have a cycle. That is kind of, if you formally speaking, you can talk about inductiveness. But also, if you ask me to write a proof of it, I would kind of not write it almost. That see, we are checking at any point of time, right? At any point of time, we are checking here. Does it produce a cycle? And so how can it produce a cycle? Right. So you are right that formally proving it, it would be an inductive proof that you have to do that it is a that the fact that A doesn't contain a cycle is a loop invariant. So at any point of time, if A doesn't have a cycle, after one more loop of this for loop, it still will not have a cycle. Now, this is a place where I would say that if such a thing is asked in the exam or some other place, you don't have to be very formal about it. It's okay. We understand it that this is not a cycle. This doesn't contain a cycle. Is there anyone have doubt about this thing that it doesn't have a cycle? Everybody is convinced it doesn't have a cycle? Excellent. But what about the other thing? What about connectedness? How do you prove that the output graph is connected?
So I'm guessing that we are essentially going through all the edges in the sorted order.
Yes, we are going through all the edges.
Adding edges when it's forming a cycle. So
Yes.
for any graph, we can claim that if we remove an edge from a given cycle, the graph does not get disconnected, because like if there's a cycle, then there are two distinct paths between two vertices, and so it would not be disconnected. So from there we can claim that the graph would still remain connected because we are only removing edges from cycles.
Yes. So good. So what you kind of gave is a kind of an informal proof of this. Okay. I completely agree what you are saying, and that is the intuition behind it. But we can make it a bit more formal if you want. I saw that. Okay, so somebody says that if the graph is not connected, then the algorithm does not terminate. Now that statement is not true, because see, when does the graph terminate? The algorithm terminates when it has kind of looked at all the edges. So terminating thing is it has looked at all the edges. So it would stop after m steps or m round of the for loop. So what the question is that after m round of the for loop, why is it connected? Okay. So see, here is this kind of a proof that is. So let's prove by contradiction. See, we cannot prove by induction. Why? Because intermediate steps, the A is not necessarily connected. Right? We know that. We have seen this in this example also. Like for example, in this example, look at the red edges here. It is not connected. This is a tree, this is a tree. So there are disconnected components in the middle, right? So we cannot prove by induction. So to prove by contradiction, so let us assume that the graph obtained by the vertex set V and the edge set A is not connected. Okay, at the end, okay, finally. So that means that graph has some connected components. Let the connected components be U1 to UT, some connected set of components. So that means there must be, but the graph G is connected. So that means there must be an edge, some UV in the graph G, which connects two of these components. Right? It must be connected because the G is connected. So here also, if you want, you can make this statement even more formal. Yeah.
Are you claiming that the only reason that U and V were not picked is because we were getting cycles, but since these are disjoint connected components, that is not possible?
Exactly.
I see.
That's exactly what we were going to say. Okay. So basically, I said that consider the time in the algorithm when the UV was considered. So the graph, the algorithm looked at all the edges one by one in some order, right? So there was a time when the UV was considered. Consider that point. At that point, the adding UV to the A in the end doesn't produce a cycle because it doesn't have a cycle. It's a connected component. If I connect two components, how can they produce a cycle? So if that is not the case, then how could UV have produced a cycle in that time? So that means at that time UV would have been picked. And in that case, UI and UJ would not be different components. And hence a contradiction. Because we have assumed that UI and UJ are two distinct connected components. Okay. Any doubts, any questions about this thing, this part? Okay, I will upload the slides today, just right after the class, so that you can go over them and verify it. Okay, this is not hard. Believe me, this is not at all hard. Okay, this is just formalizing what you had in mind in some sense. Many of you had in mind. So this would just prove that the graph is connected. The fact that the graph has no cycles, that is kind of, as I told you, we don't need to go over it. It's kind of obvious. But what is not obvious at all is why is this an MST? Why is this not a minimum spanning tree? Okay, so this is something to prove this statement. We will use this exactly the same these properties that we have, that if you add an edge, you will get a cycle will formed in a tree. If you remove any edge from that cycle, you can get back a tree. And these are the two things that we need. Right? So let's try to prove that the graph that we have at the end is an MST. Okay. So let T be the output, meaning that's the final graph, right? So V comma A kind of stuff. So that is the final tree that we output. And let us assume that T min be an MST. This is some MST. I don't know what MST is. Some MST. So we can kind of assume that, oh, see, T is not an MST. Okay, very good. So consider the smallest edge. Smallest weight means the smallest weighted edge. That is in T min and not in T. Okay. So T min and T must be differing somewhere in some edge. So consider the edge that is in that MST, but not in the graph that we have produced. And let E be the kth smallest edge. Okay, so some kth smallest edge, right? Good.
Sir?
Yeah.
Sir, what is kth smallest?
So T min has set of edges, right? N edges,
Yes.
N minus 1 edges.
Yes.
Right? If you order the edges in T min in a ascending order, E is the kth edge in T min.
But E fast assumption is E be the smallest edge.
Smallest meaning right. E with the smallest edge.
So
So
in
smallest
ascent-
meaning all the other edges. E the 1 to k minus 1 edges are all in T. See, T mean is different from T, right? Doesn't mean that
Yes.
all the edges are distinct, right? So T mean has some edge that is different than T, right?
But
So maybe I have you have given me a edge, a graph T, and the T mean is a MST. The first 10 edges are there. First 10 edges in T that we have for first 10 edges in T mean is also there in T.
okay.
Okay, but the 11th edge in T mean is not there in T.
Oh,
So E is the 11th edge.
E
Is
with
that
11.
Okay.
Okay. Okay.
So all the edges that are weight smaller than E, for those edges, T mean, all the edges in T mean is there in T.
Okay.
Fine.
Yes.
So now let's see, is the K smallest edge? Okay, so sorry, I've written it in this E to the Q. Okay, and now consider E0 be the kth smallest edge in T. So T is a different tree, right? So the kth, the 11th smallest edge in T. The first 10 edges, first 10 smallest edges in T mean is there in T, right? But the 11th smallest edge in T mean is not there in T. Correct. Fine. Consider the 11th smallest edge in T. That will be the E0. Okay. Now, first thing I want to claim is that the weight of this edge must be less than the weight of weight of E0 must be less than the weight of E. That means the 11th smallest edge less than or equal to 11th smallest edge of 11th smallest edge of T must be less weight than the 11th smallest edge of T mean.
If it wasn't, the algorithm would have picked UV at the 11th step. Yeah.
Exactly. If it wasn't, then the algorithm UV would have been picked. See, the first 10 edges was picked, right? So consider when the 11th edge, when UV edge came, then our algorithm would have picked up UV. Why didn't it not pick UV? So that cannot be, right? It did not, you kind of decided to skip UV and then continue to U0 V0. So that is not possible, right? So this is, so it must be the edge weight of E0 must be less than the edge weight of EV. Okay, that's the first thing. Good. But this is not over, right? Okay. Now, what we will show is that you started with T and we had this T mean. We will show that there exists another MST that matches with T on the first K edges. So you started with T mean that matched with T on the first 10 edges. The 11th edge was different. I will produce you another tree which will match on the first 11 edges then. If I can do that, I can slowly increase. So basically, I'm just talking like an induction kind of stuff like that. Or if you want to set it up as a contradiction, you can also talk about it. That okay. So in some sense, somebody has. So I have given you a graph T. Somebody has said that see, here is another graph. This is the. So your graph is not an MST. Here is my MST. It matches with you with your graph T on first 10 edges, but not on the 11th edge. Okay, very good, possible. But then I can produce you another MST. I will take your T mean and produce you another MST, which will match with my T on the first 11 edges, one more extra edge. And then by recursive way, I can slowly say that it will match with everything. That's the main idea of this whole thing, right? So how can we show this one? See, what do you think? Are you guys with me? Any idea how do you kind of prove this? Hello? No idea? So this is exactly what we did when we talked about the second smallest stage. Sorry, not good. Okay, so I have not, it's not written here. So let me yeah. So what do we have here? So I had my tree T. So the tree has say age E1, E2 till E10. Then it had E11, E12, and so on and so forth. So I assume that this is all less than this. I mean, when I'm writing it less, that means their weights are smaller or equal to. And you have given me a T min which matches the first 10 of them match E10. But this then there is a E say prime 11 and they are different, right? So E prime is not equal to E prime 11 is not equal to E11, right? Very good.
Connect T prime 11, that will create a cycle, and
Right.
in T, and then at least one element from that cycle must be not in T min, because otherwise T min will not be a tree.
Exactly.
Yeah, and then you consider removal of then E11 prime and that one element, and that will result in a, yeah.
Yes. So consider this graph, the whole graph G. In this graph, how was it organized? Let's say, of course, I was E1 to E1, then there was E2, then there was E10, then there was E. So as we kind of pointed out, that weight of this E11 must be less than or equal to weight of E11 prime, because else when if this is not the case, in that case when E11 was being considered, so that means in that case E11 prime would be less than E11. So E11 prime, so if not, okay, so if not this, then in that case this is how the ordering of the edges will be, and in that case the algorithm would have considered E11 prime before going to E11, and in that case it would have picked E11 prime, because at that time, see, this doesn't have a tree. By adding this E11 prime, of course we don't have a tree, because E1 to E11 prime is a part of a tree, so it doesn't produce a cycle, right? So that means the algorithm would have picked E11 prime at that time, but it did not. So that means it cannot be, the Gruskal's algorithm did not pick E11 prime, therefore it must be that the weight of E11 must be lower than the weight of E11 prime. So that means it is like this. Any questions here so far? Hello? Hello?
Yes, sir.
Is it everything is very clear or is it very not clear?
It's not completely clear to me. I would have to go through it on my own once again.
Okay. Okay. What about the others? I mean, if you are not clear, why are you not saying it? The rest of you are still not answering. I'm assuming that you are clear to all of the rest of you.
Sir, I had some connection issues, but I got it generally. Like I would just have to go.
Okay. Okay. So of course you have to go over it at home clear slowly, but so there will be two parts. Okay. So first thing is to what we proved is that. Okay. So maybe I should write it here. So we have this one. First thing we prove is this statement, that the weight of E11 or E11 must be less than of weight of E11 prime. Okay, so I can write it here. Else, Kruskal would have no, so sorry. So Shahil, can you just say what you are writing?
No, sir. Someone asked a question. I think I. So,
okay.
Yeah. The question is that if the algorithm runs for, so can't we just say that if it runs for n-1 steps, it will eventually be connected because n-, but the issue is we don't know whether it will run for n-1 edges or not. So this proof is incorrect, right?
I mean, it will go for n-1 edges.
Yeah, right? Of course it will. But to prove connectedness, we can't assume that it will go for
But that doesn't mean anything.
Yeah, exactly. Yeah, it's a cyclic reason.
The algorithm will go over all the possible edges. But n-1 edges doesn't mean it will pick n-1 edges. If you can prove that the algorithm will pick n-1 edges, then yes.
Yeah.
Yeah, then you are done. But how can we prove that it will pick up n-1 edges? Yeah, so that's maybe another way of proving connectedness or tree. Because you have proved acyclic, if you can prove that the algorithm will certainly pick n-1 edges, then you will prove that it is connected. But that doesn't necessarily, we don't have a proof for that.
Sir, if the algorithm necessarily picks, let's say, n-1 edges, then
Yes.
can we say with specificity that it could be a tree only?
Yes, if it is acyclic, if it is an acyclic graph with n-1 edges, it has to be a tree and it is to be connected.
Okay.
Okay. But how do I know that it will pick n-1 edges? My algorithm never says that it will pick n-1 edges.
You will have to prove it's a tree to prove that to begin with. It's a cyclic reasoning.
Yes, cyclic reasoning, that's that. Okay. Okay, so coming back here, so we have first we prove that these edges of E11 must be lower than the weight of E11. And now, so that means in the graph, this is how the tree looks like. The ordering of the edges look like. There might be edges in the middle, which I don't know. But then what can be done? I can consider T mean and add E11. What happens? It produces a cycle. And note that in this T mean, all the other edges are bigger than E11 prime. So that means it of course produces a cycle. This one produces a cycle. In that cycle, all the other edges, right? So they cannot, these things cannot, there must be some other, see, I know that E1 to E11 doesn't produce a cycle because this is a part of my output. So it cannot produce a cycle. There's no cycle. So that means the cycle must contain, so there exists a cycle or containing one of E11 prime or higher, right? One of these sets. So there must be a cycle, the cycle must contain one of these things. In that case, what do? We remove that edge. Okay, so let it be that E hat. So I remove E hat from that side. I get a new tree. So I started with a T mean, which was a MST. I added something. I removed the edge from the cycle. I would get back another MST because I have added something and removed something of higher weight. So I must get an MST. So this is say we can call this one T mean prime. This is a new MST. Correct? Is the new MST. And what is the property of this new MST? This MST contains E1 to E10 and E11. So you started with the MST that matched with my output for the first 10 edges. And we ended up producing another MST that matched with the T with 11 edges. So we can continue like this now, right? We can now produce another MST that matches with my T with 12 edges, and so on and so forth. What is there to stop there? Which will mean slowly that the output that we have is also an MST. Is this any questions, doubts? I mean, this will require you to go back and think a little bit. This proof is not obvious, and that is exactly the reason why I was expecting that you guys would have studied a little bit more about the MST before coming today. But any case, is this any doubts? Any questions?
Sir, I don't understand how it's not necessary that you will go through n-1 edges.
You will go through n-1 edges. There's no doubt about it. You mean in the algorithm, right? Hello? Come on. When you ask a question, keep yourself unmuted. Who was it that asked the question? Hello? Am I audible?
Yes, sir, you are.
Yes, sir.
Who asked
Hello?
the question?
Sir, I was asking the message written in that chat box.
Yes.
I don't understand how it's wrong. Like what was the reasoning?
What is wrong? Can you just say what is wrong? The algorithm will go through n-1 edges. It will go through m edges, all the edges. But what is the guarantee that algorithm will pick n-1 edges?
Sir, if it won't pick n-1 edges, then won't it mean that our initial graph was disconnected?
Yes, so you are going in cycles, right? I mean, but why? I mean, can you just say why is that?
Sir, if it's not the case, like if it was already connected, then we already have n vertices, and if we are not going through each vertex, like if each vertex is not covered, then the edges would be less than n-1, right? Like more than n-1, since we have more cycles.
Just one second. Hello. না এখন আমি আসছি আমি টকে আছি আমি আসছি তবে hello yeah
yes
yeah so see the algorithm is going through all the edges. Okay, fine. Now it is going to pick only when they don't create a cycle. Okay, now yes, from this algorithm how can you immediately conclude that the algorithm will pick n-1 edges? I am telling you the algorithm will pick n-1 edges. That is true. But how can you prove it or say it so confidently?
You're assuming it's a tree to prove it's connected, and that's just
yes. Okay. I mean, what you are saying is correct. The algorithm will pick n-1 edges. but the proof is not obvious. Obvious meaning it is not obvious from this pseudocode. Okay. Any other questions? Okay, so I would like you guys to go back and think about the proof of this correctness of this algorithm. This is not easy. This is the first algorithm that possibly you have seen where proof of correctness is not trivial. Now, let me ask you another thing. I've already overshot the time. Maybe I should not continue. So maybe I will continue on Monday with this thing. But in the meantime, can you guys, I will just share this slides and all, but can you think about what will be the runtime of this algorithm? This would be the next thing. What is the runtime of this Kruskal algorithm? Okay. And think about the runtime, and then we will take it from there.
Sir, before you go, can you lay out the syllabus for the mid-sem? Like what will be covered?
Everything that will be done till the day before.
Okay. And we should expect questions like we're getting in the problem sheet and the assignment?
Yes.
Okay. Understood.
Yeah. So in the problem sheet, we have not yet posted any problems on graph algorithms. That we will be posting it very soon. Okay. So do expect problems from DFS, BFS, minimum spanning tree, and so on. Okay. Yeah. Okay, so let me stop here today. Please go back and read the correct proof of correctness of the Kruskal algorithm. Try it for yourself. And as I am telling it multiple times, pick up a book and read it. Okay. Unless you pick up a book by yourself and read it, it would look magical to you. You will understand it somewhat from whatever I'm saying, but you will not figure out. Instead of that, please pick up any book and read it. If you have any doubts, then you can come back and ask. Okay, this proof is not trivial. Okay, this proof of the correctness of Kruskal's algorithm is not at all obvious. Okay, so I will stop here today.
Sir, just one thing regarding MTechCS tutorial, we have not received any notice.
So tutorial is today, right?
Yes, we have not received any message regarding.
So today there was a notice. No, I thought I saw notice from, or maybe was it yesterday?
It was from yesterday's CRS tutorial.
Okay, so show me, are you there? Show me, are you there? Okay, so let me just see. I will just coordinate with the TS, and I will. They will send you a mail.
Okay, sir.
Okay, right now.
Okay.
Yeah.